Are you having difficulty wiring up or understanding limit switches or emergency stop buttons? These are limit switches of varying types, and these are emergency stop buttons or e-stops of varying types. These components are some of the most difficult components to wire up in CNC machines and industrial equipment. But these components are actually really simple because all they do is provide a signal that is either on or off, connected or not connected. This video will serve as an ultimate guide on understanding limit switches and emergency stops and the various ways you can connect them. I plan to make this particular video on YouTube to be a video that can respond to comments, and the video will be remade in response to those comments. So this video can be fluid and can be relevant at any time. So if somebody makes a comment on something that I got wrong or needs to show an update of some kind, I will remake the video and delete the existing video. So you can always go to a video that's always up to date. Let's first take a look at how these work. We'll start with the emergency stop buttons. Emergency stop buttons allow you to stop machinery at a press of a button. When the emergency stop button is pressed, the machinery stops immediately. The button will stay depressed until the button is rotated and disengaged. Each of these e-stop buttons have a normally closed or a normally open configuration. In a normally closed state, the two contacts, depending on which side is normally closed and normally open, will be disconnected. The normally closed is disconnected. These two contacts do not connect. On this particular emergency stop button, there's a normally closed state on one side and a normally open state on the other side. On the normally closed side, the two contacts here will be connected. They will be closed. On the normally open side, they will be open or disconnected. These two contacts will not touch each other. On the normally closed side, when the emergency stop is engaged, that means the two contacts will open or disconnect. It will not be closed anymore. On the normally open side, when the button is depressed and the e-stop is engaged, the two contacts will now touch each other or be closed. They will not be open anymore. Let's take a look more closely at what's going on inside of the emergency stop. You'll see that this is the normally closed state because there is a piece of metal here that is contacting the two terminals here. There is a mechanical connection between this terminal and this terminal via this piece of metal here. And when I engage the e-stop or I press the button, you'll notice that the two terminals are not connected anymore by this piece of metal. The metal has moved up, so it broke the connection between these two terminals. So when I disengage it, you'll see that it jumped back down to the two terminals. Let's take a look at the normally open side. The contacts are actually on the very top. You can see that little piece of metal here. This contact has a connection to the top, so the metal plate that moves up and down is on the down position just like it was on the other side, and when it moves up it'll contact them. So right now this metal plate is not contacting either of these connections, and when I depress the e-stop, you'll see that the metal plate moved towards these two contacts here, which connect to the terminals. Let's connect a multimeter to the e-stop and test the two terminals when the e-stop is engaged. This is the normally closed side. It's the side with the red color to it. You can use a multimeter to determine whether the side that you need to connect is either normally closed or normally open. In this particular e-stop, you can see what's inside, but in this one you can't see it. So it's good to know, without having to look at documentation for the switch, to just go ahead and use a multimeter to test it. So this is the normally closed side. Right now it shows open line. They're not connected. So when you connect these two terminals, it should show 0 or close to 0. And then when I engage the switch, it should show open line again. Let's do the same thing on the normally open side. Right now it shows open line, and when I engage it, because it's normally open, it should be open line, not connected. When I engage it, it should show 0. Let's do this with the e-stop that you can't see what's going on inside. So this would be the red side. I have no idea which one that is, if it's normally open or normally closed. This is the normally closed side because it shows 0. If we engage it, it shows open line. Let's do the same thing to the other side. All right, this shows open line. That means it's normally open. And if I engage it, it shows 0. This e-stop doesn't have the two sides. It only has 3 quick disconnect connectors on the bottom. But this one shows you which one is normally open and which one is normally closed. The connectors on the bottom show normally closed and normally open here. And you'd connect the other wire to the common, which is the C. So you'll have a C and a normally open that will connect together to provide the functionality of the e-stop in a normally open configuration, or common and normally closed for the normally closed configuration. So let's test this on a multimeter. Right now the switch is disengaged. Okay, I'll connect the black to common and I'll connect the red to normally closed. So this should show a 0 because it has a connection between them. And when I engage, it will show open line. I'm going to disengage it. Let's go to the normally open. So you can see it says open line. And if I engage it, it will close the circuit and show 0. Now let's talk about the limit switches. Limit switches are just like the emergency stops, where each of the limit switches has a normally closed or normally open option, with the exception of the proximity switch. But I'll talk about that later. This is a rotary limit switch that will engage when something hits this wheel. The benefit to this rotary limit switch is its ability to adjust this arm here outwards and adjust the rotation using this set screw. This is a snap action limit switch that also has a little roller that will engage when a part of the machine either hits it like this or slides into it like this. Let's take a look at this one in more depth. In this limit switch, the cable would first go into here, come out, and be screwed into these terminals here. These terminals have either the normally closed or normally open options. The 2 terminals on the bottom are normally closed, and the 2 terminals on the top are normally open. So let's take a look at this in more detail. You will see that there is a little plate that goes across, just like in the emergency stop button, and you'll notice that when the switch is engaged, the plate moves from one set of terminals to the other set of terminals. Since this is the normally closed side, the plate is on the bottom connecting these 2 together. And when the switch engages, it moves away from these 2 terminals, making it open. On the 2 top ones, the normally open terminals, the plate is on the bottom, so it's not touching these 2 terminals. And when it engages, it closes these 2 terminals. With the snap action limit switch, you have 3 terminal positions. These are quick disconnects, and the one on the bottom is common, the one in the middle is normally open, and the one on top is normally closed. So when you connect the common to the normally open, this is a broken circuit normally when it's not engaged, and when you engage it, these 2 have a circuit connection. These will close. And with the normally closed, these 2 terminals, the one on the top here and the one on the bottom, the common, will be connected, and once the switch engages, these 2 will break its connection. This is a proximity switch. This proximity switch engages when a piece of metal, generally a ferrous piece of metal, comes in close contact with the front of the switch. Proximity switches are a bit different than standard limit switches. You can't switch between normally open and normally closed. This particular one is only normally open. You have to power this one because it requires power to detect its limit, and this is powered between 6 volts and 36 volts DC. When you're purchasing a switch like this, pay close attention to the distance from the tip to the ferrous metal where it engages. This one is 4 millimeters. I have a much more detailed video on proximity switches, and I'll leave that link right here, or you can click the link in the description. Now let's talk about how to wire these limit switches and emergency stops to the controller, or to the system that you'll be connecting these to. We'll start with the emergency stop buttons. The way you connect an e-stop to a machine, whether it be an industrial machine on an assembly line floor or a CNC machine is somewhat controversial. You can connect an e-stop to a controller that interfaces to software and that may have signal lines, or you can connect an e-stop straight to the power that powers the device that you're trying to stop. With CNC machines, I connect an e-stop to a signal line, which is connecting to an input on a controller. Connecting the e-stop to a controller that is, say, controlling a CNC machine, one side could be connected to the ground terminal, and the other side could be connected to one of the inputs on the controller. When you are connecting to the input of a controller, you need to decide whether you're going to connect it in normally open or normally closed configuration. The normally closed configuration is the best option because if a line was interrupted in some way, then the system would shut down, which is the safest option. In a normally closed configuration, which is represented like this, a normally open configuration would be represented like this, or like this, because there's a space between the switch and the line, and in here there's a space. But here there's no space, so it shows a continual connection. In this scenario, the machine is in a state that is on and running, and if somewhere along the connection there is a break, but the break didn't happen at the switch, the machine would shut down, which is the safest option. But in many controllers, you may not have this option. You may have to go with a normally open scenario. In the configuration of a normally open switch, if there was a break in the line, in the connection, anywhere between the ground and the input, other than where the switch is, the switch would become useless at that point, because if you try to depress the switch and close this line, you'd still have an open section here, so the switch would not function or operate as intended. If you want to use an e-stop to cut off the power source to the device you're trying to stop, you want to make sure that you are well within the specifications of the e-stop limits with the max voltage and max amps. On this e-stop, the limit is 440 volts at 10 amps. If you wanted to wire this up to the power source, say you're using a standard earth ground, neutral, and live 110 volt system, you would connect the live through the normally closed side of the emergency stop switch, and the neutral would go straight to the power supplies and the earth ground would go straight to the power supply. So when the e-stop is engaged, it will cut the circuit to the live connection, causing an interruption in that supply. I wouldn't use this option unless you had no software and controller on the machinery that you're connecting this to. For instance, if you have machinery that doesn't use a controller and software and doesn't have inputs to stop the machine, then you can use this option as a fail-safe to cut the power if something happens, if an emergency exists. There are a lot of wiring configurations for limit switches, and that's what makes the concept of limit switches and connecting limit switches to controllers so challenging for people. I'm going to represent the normally open limit switches like this, and I'm going to represent the normally closed limit switches like this. Normally open limit switches need to be wired in parallel. So let me show you what that looks like. Limit switches will connect to two different terminals on the controller. One will be called ground. Sometimes they'll connect to 5 volts, but in this scenario we'll call this ground. The other terminal will be an input terminal. Normally open switches need to be connected in a parallel fashion. So a parallel connection looks kind of like a ladder. I'll draw the switches here. So let's go ahead and connect 3 switches on a single input. All of the switches are going to connect to the ground, and all of these switches on the other side are going to connect to the input. You'll notice that there is a space between both of these connections all the way through. So this is like just having one line here and one line here, and there's no connections in the middle. Once there is a single connection, let's say this switch engages, there is now a complete connection between ground and input. So only one of them engaged and you have a closed circuit. If this one closed, you can see that you have another path to the input and ground. So the circuit is closed again. So no matter which one of these switches is engaged, it will close the circuit. because these switches are wired in parallel. In the case of this type of wiring and putting 3 switches on a single input, it's really just to provide a limit switch condition or a limit condition where you need the machine to stop when the machine hits a limit. Let's say this is one of the limits. It hits the end of a machine and the machine stops because it found a closed circuit between ground and input. You can even put one of the emergency stops on this input with other limit switches because it's just serving as a way for the machine to stop, just like a limit switch would. With an e-stop or a limit switch, the software knows exactly what to do and what processes to stop for a particular condition. Now let's talk about a normally closed scenario. Let's put the same terminals, ground and input. With a normally closed scenario, we're going to connect them in a serial fashion, not parallel. So I'll draw the switches. I'll use 3 switches like I did before. So you're just connecting it in a line. And in this scenario, you already have a connection between ground and input because there's a closed connection. It's normally closed, so there is a closed circuit. If only one of the switches engages and opens, the circuit now becomes open and the circuit is broken. And as I mentioned earlier with the emergency stop and the normally closed being the safest option, in this scenario, they're all closed, normally closed, and if something happens to the line somewhere between ground and input and a line was broken for some reason, the machine would halt and stop its processing until that issue was fixed. Some controllers allow you to have a discrete limit switch on its own terminal. These terminals would be something like X++, X-, Y++, Y-, and you would have a limit switch to the X++, which would be the far end of the X-axis. The X-, would be the near end of the X-axis. The Y++ would be the far end of the Y-axis, and the Y-, would be the near end of the Y-axis, and so on. The Z-axis, the A-axis, and so on. And these would just have its individual limit switches. So you could have normally open or normally closed in these scenarios, whichever the controller requires. I'll make these normally closed, and so on. If you had limited terminals and they were just inputs and so on, you'd normally have more than one limit switch or home switch on the individual inputs. But you have to be careful with the software that you're using may require the home switch on its own individual input. For instance, let's wire these as normally open. So we look at a little bit more of a complex situation. So let's say the input number 1 is for the X-axis. I want to make sure that I separate the X, Y, and Z axis on its own input. So I'd normally have only 2 limit switches on a particular axis, and one serves as the home switch, and that would be the X-. So it would serve as home and as a limit in case it bumps into the end of the axis by accident. So let's say this first input would be the X-axis, this would be the home and the X-, and this would be the X++. The same thing with the input number 2. Let's do the Y-axis. 2 open switches. This would connect to the ground, and these 2 would connect to the input number 2. And one would be the X-, and the home switch, and one of these switches would be the Y-, and Y home, and the other one would be Y++. And the same thing with the input number 3, would be for the Z-axis and having 2 switches. You could put the emergency stop on its own input, or you can add it onto one of these if you wanted to. So let's take a look at these configurations in wiring and what kind of wire you need to use when you're connecting limit switches to controllers. The cable or wire that you use is really important. For limit switches and e-stops, 2 conductors is sufficient, and the gauge around 22 to 24 is fine. But more importantly, making sure that it's shielded will increase your success in making sure that the machine will complete its jobs without it stopping for reasons of electromotive force, electromagnetic field, causing electromagnetic interference. Electromagnetic interference, or EMI, is a condition where the voltage levels, let's say from 0 to 5 volts, can cause noise within the signal line of 0 to 5 volts. Let's pretend this is running along at 0 volts and you have some EMI. It's causing some interference here, and there is a section within the 0 to 5 volts that the controller doesn't know how to process. because this little band here between the 0 and 5 volts is like a no man's land. And when interference gets into that area, and worst, causing it to go all the way to the 5 volts, can cause your signals to make your controller think that it's tripped or engaged one of the switches. The way to minimize that is to use a shield around the two conductors. And then there's another conductor here that connects to the shield all the way along the cable. This conductor needs to be taken to a ground, whether it be earth ground or a ground associated with the switches, in my experience has been fine. I tend to put it to the DC ground that is related to the switch, so I don't have any other interference or any other voltages that can be created from the machine going into this shield. But what causes the EMI in the first place? Because most likely industrial equipment or CNC machines have motors, and motors give off the EMI, electromagnetic interference. In most cases, motor wire is going to look more or less like this. It's going to have a cable with 4 conductors in it. And if you run the cables in parallel like this, or even with some space between them, the signal wire is more than likely going to get interference from these wires connected to the motor. But with this shielding, this will minimize the electromagnetic interference that this will give off. If you don't have shielding on your limit switch cabling, then you want to make sure that you don't run motor wires in parallel. You can intersect it, but you want to minimize the wires getting close to each other in the first place. An even better option would be to use motor wire that has shielding as well and has a conductor that is connected to the shield throughout the cable. This way, it won't matter as much how you run the wires through the machine, but it'll minimize the interference that the delicate signal wires will receive. In the motor wires, this is the conductor that is connected to the shielding, and this conductor is also grounded to the DC ground that's associated with the motors. So how do you take switches and connect them to a cable like this, where you have 2 conductors and then a third connected to the shielding? The way you do this is going to differ depending on your normally open or normally closed configuration. So this is a normally open switch. I'm going to put a couple of them here. And let's say this is the contacts that you would connect the switch to. Let's go ahead and put a box around here just so it looks like it's a switch. So let's put the terminals here, input and ground. And for the normally open, we talked about wiring them in parallel like this. So if one closes, a circuit would be formed in that instance. So let's just get rid of a couple of these wires here, or connections, and let's put the cable here. I'll just represent the cable jacket as 2 black lines, and we have a black wire. I'll use the black for that. And this would be cable of indeterminate length here, between here and here, because that could be a long distance. And then you will have a red wire inside of that cable, and we'll connect the red wire to the input and the black wire to ground. Let's go ahead and put a green wire here that's connected to the shield. All you're going to do is connect the red wire to the first switch, then the red wire here through the cable, and then the red wire to the next switch. And this will connect to the input. The black wire will connect to the other side of the switch and back to ground. And on the ground side, the black wire, you're just going to do the same thing with the green shield wire. It's going to go back to the ground, and it's going to connect to all of the places that's connecting to the black wire. What if you wanted the switches in series for normally closed? So let's draw a couple switches. These are normally closed. I'll just close the switch. I'll put another switch over here. So this would be, let's say, common and NC, common and NC on the switch. And just like the other side, we have the input and ground. And we know that we connect the wires in series, starting from ground or input and go through and then bringing it back to ground. But since there's a cable, we want to just use part of the cable, then the switch, cable, then switch. So how do we do that? Just like this side, let's put the cable jacket. This could be at any length between here and here. And we do the same thing over here. I didn't give myself much room here, but that's fine. So we have a black wire inside the cable, we have a red wire inside the cable, and we have the green conductor that connects to the shield. In this case, we're simply going to run the black wires around, and it's going to terminate to the end here, and it's going to hit the ground. So the black wire is not going to connect to any of the switches except for the very end terminal of a switch. The green wire, or the conductor that is connected to the shielding, is going to connect with the ground as well, and it's going to go all the way back, just like the just like the black wire. Just like the black wire. And it's going to connect to the end of the last switch. The red wire is going to connect to the input and is going to connect to the first switch, and then we'll connect this part of the cable to the next part of the switch, and so on. Now let's show an example using real wire and real switches. Now let's show an example with real wire cable. Now let's show an example of, oh my God, really? Don't eat the cable. Let's connect two limit switches, and using a cable, we can test the results with a multimeter. I'll start with a normally open configuration, which is wiring these two limit switches in parallel. The end that connects to the controller, the black conductor, will be connected to the shield, and that will go to the common or ground on the controller, and the red will go to the input. Somewhere on this cable, I'm going to connect one of the limit switches. So I'm just going to cut it because in a parallel connection, we're going to use both of these conductors and connect to the limit switch. I'm going to take the other end and remove the insulation and do the same thing. I'm going to take the two reds, connect those together. I'll use a small red quick disconnect. And I'll take both blacks and both shield conductors, connect them all together. All right, I'll take the black and connect it to the common. It really doesn't matter which side you connect it to. It could be the common or the normally open. And the normally open connector is here. Okay, so already this could work even though this end is still disconnected and not having a switch at the end because it's open. And at the end, we're just going to connect the black and shield to the common and the red to the normally open. Okay, I'm just going to plug in the common or ground wire and the normally open. So we have two switches connected at various points in the cable. Now we can test at this end with the multimeter. We want to set this to ohms. So right now we're looking at open line, and if we connect these two together, we have a closed connection. Put the black lead on the black wire and the red lead on the red wire. It doesn't really matter which one you connect these two because we're just testing whether it's connected or not. Because these switches are in parallel, if I engage either one of them, it should make a connection. And it works. Now let's connect these two limit switches in a normally closed configuration. To place a limit switch at some point in this cable, you want to try to get the access to the red cable, but that's not very easy to do. Unless you're an expert at cutting the insulation off of a cable at a certain distance and getting access to the red wire, then you can try to do that. But the easiest way to do it is just to cut it and expose all of the ends and just connect the black and shield conductor together and then just use the red conductor for the switch. So let's go ahead and try to do that. The two black conductors and the two shields are going to all be connected together. You can do this with solder by soldering it all together, or you can use a butt connector, or you can use one of these kinds of connectors that is a soldering connector, and it also makes a watertight seal in the end. Although this doesn't need to be watertight, and it probably won't be watertight because you have two conductors going in. So let's go ahead and put one side in and then the other side. And you just need to heat up that middle section. I'm going to use a heat gun as opposed to fire to melt the solder and heat shrink this tubing. You can use like a burner like this, but you risk damaging the insulation. You want to make sure to let this cool before you start handling it. Insulation is very soft at this point, and you want it to let it harden. You can still feel it's kind of sticky, so it feels good now. And on the red conductors, I'm just going to use the same style of quick disconnect. So we can go ahead and put the first switch on. It doesn't really matter which side goes on the common, but you want to make sure to use the normally closed side. Okay, so the only reason you're putting a switch into a section of the cable like this means that you need to also have another switch at the end. If you're only going to put one switch on a cable, you just want to put one on the end. So let's go ahead and put the last switch onto the end. All right, and we're going to connect this just like we did on the parallel connection or the normally open connection. A quick disconnect on the end here for the black and the shield, and we'll put one for the red conductor. Now, it doesn't really matter which one you connect the red to. It can be the common or the normally closed. I'll put it on the normally closed, and then I'll put the black one on the common. So now we have two limit switches in normally closed configuration. So let's go ahead and test it. Put it back in ohms. I'll connect the black and shield to the black and the red to the red. And you'll see that we have a connection because it's normally closed, meaning there is a connection connecting the black and the red until I engage one of these switches. So let's do one at a time. Let's try this one. It looks like we have an open line, which is now we have disconnected the line. I unengage it or I release the limit switch and it goes back to connected. Let's try the next one. And it has an open line connection here. So this one worked successfully. And to bring my point across, if something happened to the connection somewhere along the line, like let's say this line got disconnected from the controller, you'll see it's open line, and that means that the machine would not start or it would be disabled in this condition. You'll see nothing happens obviously with the switch. So in this case, you know there's something wrong with the line and you want to make sure that you diagnose that problem before you start the machine, obviously, because you won't be able to start the machine. I hope all of this helps, and if you have any questions, please leave me a comment in the comment section, and make sure to like, or if you haven't subscribed yet, subscribe to the channel. Thank you so much.